This lesson is solving special systems. With this section, there are some definitions. We have consistent system, which is a system with at least one solution. So a consistent system has one solution. An inconsistent system is when we have no solution. You sometimes might see in this section an independent system that has exactly one solution. And the graph of an independent system consists of two intersecting lines. Dependent system has infinitely many solutions, and the graph of the dependent consists of two coincident lines. Also in this section, we're going to have to label, we're going to have to classify whether systems of equations are consistent and independent, whether they're consistent and dependent, or inconsistent. So when we're solving with systems of equations, we're going to look at how many solutions they have. Exactly one, infinitely many, or none. We're going to look at the description of the equations. So when we set up the equations, do we have different slopes? Is it the same slope and same y-intercept, meaning same exact equation? Or do you have the same slope but different y-intercepts? So notice these different solutions and descriptions. Based on that, you're going to be labeling the system of equations as consistent and independent, consistent and dependent, or inconsistent. So for instance, if you had two equations that had completely different slopes, that means these lines would be intersecting, and that would be a consistent and independent situation. If you had two equations and you solved and they had the same slope and the same y-intercept, the same exact equation, that's a coincident line with infinitely many solutions. And when you have, which we call consistent and dependent, and when you have equations that have the same slope but different y-intercepts, that's inconsistent, and that means the lines are parallel. So let's look at some equations and solve them to determine what kind of system of equations this represents. So example number 1 says, show that y equals x minus 4 and negative x plus y equals 3 has no solution. So what I'm first going to do with this is I'm going to substitute this x minus 4 into the y to my second equation, because we have solved y equals x minus 4, so I'm going to take that negative x plus my y. We said y is x minus 4 equals 3. Well, let's look at this. When we combine like terms, that negative x and x, that becomes 0. So what I'm left with in this equation is negative 4 equals 3. Is that true? No, negative 4 does not equal true. So this is not true. So that's why this is a no solution problem. In the notes here I'm pulling up, so as it mentioned, you're going to substitute x minus 4 in for y to solve the second equation, and the second equation to solve. So when we solved it, we got negative 4 does not equal 3. So for this system, there is no solution. Let's go on to the next example. It says show that these two equations have infinitely many solutions. So y equals 3x plus 2, 3x minus y plus 2 equals 0. What we're going to do for this is we're going to write both equations in the slope-intercept form. Remember, that's the y equals mx plus b form. And the lines, we'll notice that the lines are going to have the same slope and the same y-intercept. So let me rewrite this. The first equation is in the slope-intercept form. So we have y equals 3x plus 2. But the second equation is not. We need to put it in that form, y equals mx plus b. So we have 3x minus y plus 2 equals 0. Let's first subtract 2 to each side. So what I have is 3x minus y equals negative 2. I now need to get that 3x over to the right, so I'm going to subtract 3x to both sides. So what I have is negative y equals negative 3x minus 2. You can't have a negative variable, So we can pretend there's a 1 in front of y, so we divide both sides by -1. So what I have left now is y equals -3 divided by -1 is positive 3x. -2 divided by -1 is positive 2. So I have y equals 3x plus 2, y equals 3x plus 2. They are the same exact equation. That means they are coincident lines. And so for this situation, these two equations would be coincident and dependent based on that chart that we looked at on the third slide. Now we're going to classify the systems and give the number of solutions. So you really need to look back at the chart here, this chart, to help determine how many solutions we're going to find. And then we need to classify whether it's coincident and independent, coincident and dependent, or inconsistent. And the first two examples that we solved for, we found that there was no solution, so there was nothing happening. The second equation we solved for, or the second example we solved for, we had coincidence lines where we had the same slope and same y-intercept, so it was a coincident and dependent variable, or dependent classification. So now let's look at our third example where we're going to have to classify the system and give the number of solutions. So for each of these, we're going to set it up in the slope-intercept form. And let's, by setting each of these up in the slope-intercept form, we're going to determine what kind of equations they are. So when we look at the first one, we have 3y equals x plus 3. We're going to divide 3 to each side. So this first equation here, we have y equals 1/3 x plus 1. Because 3 divided by 3 is 1. 1 divided by 3 is just 1/3 x. Let's look at my second example. I have negative 1/3 x plus y equals 1. Let's add 1/3 x to each side. So what I have is y equals 1/3 x plus 1. Notice these two equations are the exact same. So for example A, this is a consistent and dependent. So this number of solutions is that they are the same equation. And we can say that the system is coincident, is consistent, and dependent. So that's for A. Now let's solve for B. I'm going to erase part of A so I can write out B here. For B now, you need to put both of these equations in the slope-intercept form, y equals mx plus b, to determine how many solutions it has and to classify the system. So for the first one, we have x plus y equals 5. Subtract x to each side. So what I have is y equals a negative x plus 5 for the first equation. The second one, we have 4 plus y equals negative x. I can subtract 4 to each side. So I have y equals negative x minus 4. Notice both of these equations have the same slope, but they have different y-intercepts. So we can say that the lines have the same slope, but different y-intercepts, so therefore they are parallel. And so this system is going to be inconsistent, has no solution when they are parallel lines. So the system is inconsistent and we can say it has no solution. So that would be the answer to B. Moving on to C. Let me erase part of B here so you can see C. So for C, we're going to put both of these in the slope-intercept form. So we can, for the first equation, distribute that -2 to each situation inside the parentheses. So we have y equals -2x plus 2. The second one, we have y equals -x plus 3. And since these lines have nothing really in common, the slopes are not the same, the y-intercepts are not the same, we're going to say the lines have different slopes So when they have different slopes in this situation, they're going to intersect. Where we left off too was the lines will intersect, and since these lines intersect, we say that the system is consistent and independent. And when they do intersect, we say that there is one solution taking place. So for all of these equations, we're putting them in the slope-intercept form, and then from there we're classifying the system and telling how many solutions that they have. And what's going to help you classify this as well as looking at that chart that I showed you on the third slide.